Hi, everyone. My name is Clara Cogswell. I'm the community support hydrologist at CUAHSI. And I'm really happy to be able to introduce our amazing lineup of speakers today. First, we have speaking Taher Chigini. And if you want to just introduce yourself and state your affiliation, and then share your screen, you can begin.
Can you see my screen?
Yeah, looks good.
Great. Hello, everyone. My name is Taher Chigini. I'm a PhD candidate at University of Houston. I would like to thank CUAHSI for giving me the opportunity to present my open source project. So today I'm going to present a suite of open source Python packages that I developed over the past 2 years called hydrologist. So in hydrological studies, it's common that we require accessing different data types from various data sources. For example, we must require vector data like street and buildings, and then the raster data such as vegetation, land use, land cover, and then we want to integrate the data and carry out our analysis. So a common framework is as follows. These datasets tend to be large in size, so you'd have to download the entire dataset on your local machine, subset the data to your region of interest, do some pre-processing and carry out your analysis. And then if you want to share your research with your colleagues and peers, then you might end up having to upload a sizable amount of data to some remote server. So there are two main challenges with this approach. First is that you require a large, relatively powerful state orchestration for handling these large data sets. And then also when you want to share your results with your peers and colleagues, doing it in a reproducible and extensible manner can be difficult. So that's where web services come in and can help with these two challenges. What are web services? We can think of it this way. Like previous approach, all these data sets are on a server, on a cloud, but instead of downloading the entire data set, these web services allow you to only request for a subset of these data sets. And they can even do some pre-processing or some common GIS operations on the server side, and they kind of give you the results that you only are interested in. There are several web service protocols. They have been around for a couple of decades, but over the last decade, they have been more common in the geospatial communities. So as I've mentioned, there are several web service protocols, each of which has their own language. And the way that the user can communicate with these web services are through their application programming interfaces, API. But as you can imagine, one of the challenges or the main drawback of these web services is that for non-technical scientists like us, working with these types of web services can be involved and a tedious task. So that's where hydrologist comes in. hydrologist provides the user with a much more user-friendly API and takes care of all the complexities and difficulties and keeping up with the technologies as they come in related to web services. So hydrologist has 8 open source Python packages. All of them are MIT licensed and are available on GitHub. The source code is available on GitHub. And contributions are most welcome. You can click on the link here, so you can go to see what are the ways that you can contribute to all these packages. So I'm going to give you a brief overview of each one of these packages and what you can do with them. So PyNHD, the first one is for navigating on substantive national hydrography data sets, for example, river networks or watershed boundaries. Py3dep is for accessing topographic data like DEM, slope, aspect at any resolution. PyGeoHydro provides access to several data sets like soil, stream flow, gauge stations, national inventory of dams, water quality, hydroclimatic, hydroclimate, data network, land use, land cover, camels, and actual transpiration. PyDemit is for accessing the DAMIT dataset, which is climate data at daily, monthly, and annual time scales. And the hydrosignatures is a collection of tools for computing hydrological signatures. The last three packages are essentially the engine of these 5 packages. They take care of all the web service calls, sending the requests and returning the responses in some formats that we hydrologists are more comfortable with. So most users won't be dealing with these 3 low-level packages because they are mostly a dependency for the other 5 packages. So most users are going to be using the other 5 packages, which are high-level APIs and are really easy to work with. So the thing that I mentioned are just a very brief overview of the capabilities of HydRiver. There are many more tools and other things that you can do with the packages. So I highly recommend you to check out the website. You can see I put a lot of examples, and you can check out the API references so you can get a better understanding of the capabilities of HydRiver. So I'm just going to give you a very brief application of HydRiver for hydrological modeling. In this example, I chose the HiMod hydrological model. We want to calibrate this model using HydRiver packages. You can find, I'm not going to into the scientific details of HiMod model, but HiMod, I provided a link to the paper and also the source code that I'm using for calibrating the model. But there are 2 things that I want to mention. First is that there is no soil component here. There is no snow component here. So we need to select a watershed that doesn't have, that is not impacted by snow significantly. And also, since this is a lump model, we want to select the station or watershed that is with the drainage area less than 500 square kilometers. So in order to do so, we start by getting the CAMELS data sets. With just one command, you can get the CAMELS data set. And then now we want to filter the data. As I've mentioned, we want to make sure that is not impacted by the snow significantly. So a snow fraction should be less than 10%, and the area should be less than 500 square kilometers. So we filtered the data, we get the first station. Now we want to get more information about the watershed and its properties. So we are going to use PyGeoHydro and PyNHD to get the basin geometry and also some information about the data set. Again, with just 2 lines of code, you can get access to all these data easily. You can see here that in this example, the name of the station is Robinson River near Locustdale, and there are some other information here. And we can plot the watershed geometry, the basin geometry. Next, we want to get the stream flow data. Again, with just using one function, you can getting stream flow from PyGeoHydro. You can get a stream flow for many stations. You can pass on any list of stations and you can get the results back. Next, we want to get the climate data using PyDAMIT. So climate data, you can get all the precipitation temperature, all the data required, and also additionally, PyDAMIT can compute potential evapotranspiration using 3 methods. For this example, we are computing PET using Hargreaves Somali method. So we just one line of code, we just pass the information and then just say that I want the PET to be using this method. Now here is like a plot of the gridded data for the watershed. Next, because it's a lump model, so we want to take an aerial average of the climate data. So we use the X-array that was returned, the data set that was returned, and we just take the aerial average. And next, what we want to do is that instead of calibrating the soil storage, because we have access to the soil data, we want to estimate it a priori. The way that we can do that, we can use PyGeoHydro to get the soil porosity and then get the soil thickness. And if we just multiply these 2 together, we can get the storage, and we take the aerial mean or aerial average of the soil storage, and we can use it as an a priori estimation of the soil parameter. Now that we have all of our required data, we just we want to calibrate and estimate, we want to calibrate the other 4 parameters. So we use SciPy, and we just calibrate the parameters. Now we want to see how the model performs. We can use the hydro signatures package to generate some of the hydraulic signatures, and then we can use PyGeoHydro to plot the data regime curve and then flood regime curve, and also the flow duration curve to measure the performance of the model. So you can see here that with just few lines of code, we were able to calibrate this model, and it's really easy to scale this model. If you want to calibrate many more stations, you can easily go back here and then change the number of stations. Instead of one station, you can pass a list of stations and then just rerun the code, rerun the notebook, and you can easily scale this operation to more number of stations. And another thing I want to mention is that there are many more capabilities, as I've said. So feel free to check out the website, and this notebook is available. You can download the notebook. Is one of the I put it as an example in the HyRiver website, so you can download the notebook. You can easily change whatever you want to change in this notebook and use it as your own in your own research. So, and also, as I've mentioned, contributions are most welcome. So feel free to check out this document, and also you can reach out to me via my email. Yep, that's it. That's it for me.
All right, thank you so much. We have a question in the chat for you that we'll get to in the moderated question period at the end. Next, Aniruddha, will you share your screen and state your affiliation, and you can begin your presentation.
Is my screen visible?
Yeah, it looks good. It's in,
Yeah.
there you go, it looks good.
Hi, so I'm Aniruddha. I'm from Indian Institute of Technology, Roorkee. So I'm currently a PhD student, but this was a part of my master's thesis where I was using laptop to model for estimating glacier thickness. So the code that I had used for estimating the thickness, I've just compiled it and converted into an R package, and it's now uploaded on the GitHub. So you can use the QR code for just checking out my repository. So it's a GPL3 open license, and the authors are me and my supervisor, Dr. Manoj Jain. So moving forward, so why GLAPTOP 2, and initially why glacier thickness model? So it serves a lot of purpose. Most importantly, for checking out the glacier thickness, getting an estimate of the glacier volume, the water content in the specific glacier, for future projection of runoff of the basin or of the watershed the glacier is a part of, for checking out the future projection of the glacial lakes that can be formed when the glacier is melted. So why GLAPTOP 2 model? Because it follows the principle of shallow ice approximation and assumption of perfect plasticity, which makes this model very simple to use. It has a very minimum data requirement, which is only the glacier DEM. And very recently, it has a self-calibrating feature which has been found out. It's not by me, but I will discuss further with it. So moving on with the model algorithm and the model calibration. So these are the three basic equations which are used. The first equation, which says how we can estimate the glacier thickness. It requires the value. It requires average basal shear stress, and most important, the mean slope of the glacier, and also the most important parameter, the shape factor. So now the biggest problem is the way to calculate shape factor. If you see this equation third, it also uses the height of the glacier. So there is no solution to this, because for thickness estimation we need shape factor, and again for finding out shape factor, we need the thickness values. So basically, this is an iterative method, and as of now, no solution has been found yet. Many of them has used trial and error. Many of the papers have used this very specific value. The current method, which was found out by Ramshankar et al., what he had done is that he had used shape factor values from 0.6 to 0.9, and he had averaged it to find out the glacier thickness. Using that thickness values, the shape factor was derived. So based on the model that he had, that Ramshankaran has, the calibrating procedure the Ramshankaran has concluded, it was seen that the model was performing way better than the other methods. So let's just move into ahead with this. So as discussed, model it requires quite simple inputs, DEM and the glacier outline. So what it is done actually is that the glacier boundary cells are given a value of 0. The gray cells that you can see are the glacier inner cells, and there are the glacier adjacent cells which are given assigned a value of 15. So random selection of the glacier inner cells are done, and an n by n buffer is built around each of the randomly selected cells, using which the mean surface slope is calculated. Once the mean surface slope is calculated, selecting a specific value of f, the height of that certain cell is derived or is estimated. Similarly, the step is repeated for all the randomly selected cells. Once we find all those values, we use the IDW interpolation for finding out the thickness of the glacier. Now this method is repeated 3 times and it gives the final thickness estimate of the glacier. So what happens is that, as discussed, we use values from 0.6, 0.61, 0.62, and similarly 31 values of shape factor to get a value of 0.9 to get the average thickness. The average thickness, when it's estimated, this is how the calibration works. Along the glacier central flow line, the central flow line of the glacier, certain cross sections are drawn, and for each cross section, the width and the thickness of the glacier at that cross section along the central flow line is used. Width and the height of the glacier along the central flow line is used. And similarly, when it is averaged over all the widths or the cross sections that we have considered, we are able to get the required shape factor and we get the thickness of the glacier. So now this is the package that I've developed in R. Very simple, 2 functions only. First function for estimating the glacier thickness, two most important inputs, DEM and the glacier outline. Then you have the values that you can give: G, which is the gravitational acceleration, which is rho, the density of ice. Default value I have used as 900. You may change and give your own value. The h dot min, which says that the minimum elevation difference in the buffer. So when we were selecting the buffer was allowed to grow until the minimum elevation difference in the buffer cell was 50. The default value is 50 because it was calibrated by some paper already, but it gives you the freedom to change these values and check out other possibilities. RC is the other input, is the other argument of this function. RC is the fraction of the randomly selected cells that you can select or pick out from the glacier inner cells. One more one more argument is the f range, the range of f, the thickness for the range of f values that you want. So the default value which I've given is from 0.6 to 0.9 at an interval of 0.01. However, you may select only one value or you may give a different range as per your need. There is one more n. N basically means the number of thickness estimates for a particular value of shape factor. As I said, as shown in the presentation, we had used 3. So the default is also 3, but you can change it for your own purpose. Now IDW, this is the power of the IDW. This IDW.p, this argument shows the power of IDW, and in default I have taken as 3 because this is what it was calibrated till now. You can check give a different value and check for yourself. HGA is the glacier adjacent cells, which has been given a default value of 15. Now again, this is also calibrated from the previous papers. And this n cores is the number of cores of your CPU which you want to assign for this task. For it is mainly used for this IDW processing. It depends. For safety, I have ensured number of cores of the CPU -3, but you can give as many cores as you want. So the outputs that you actually get from this is two outputs. One is the list of the average. One is the average thickness. Like if you maybe have given a range from 0.6 to 0.7, you will get maybe 11 thickness values. So the average thickness will have 11 values of thickness, and sorry, it would be the average of thickness, and thickness shape factors would give you the each of the 11 thickness of the glaciers. The second function is the calibration of GLAPTOP 2. So the two important arguments are glacier thickness, which would be the average glacier thickness that we have calculated or estimated in the previous function, and the cross sections. So the cross section is something that one has to draw from themselves and then import it, and based on those cross sections, the calibration would be performed. So this is an example code. In the first chunk, if you see, I am just creating a sample dem. You can import it if you have. The second here, I'm creating a sample shapefile of the glacier boundary. If you have, you can import it. So this is giving some inputs, and for calculating the thickness. Here I am again drawing some cross sections, some hypothetical cross section using code, and then I'm calibrating and I'm getting the calibrated value of the shape factor. So these are the two references, mainly the papers that I had followed for preparing this. And yeah, that's all from me. Thank you.
All right, thank you so much. And next up, we have Danielle. If you want to share your screen and let us know your affiliation, and you can go ahead and begin.
Okay. Can you see it okay?
Yeah, you're a little bit quiet though.
Okay. I'll speak up. It's is that any better?
Yes, that sounds better.
Okay, great. We'll try that then. Thanks. Hi, I'm Danielle Hare at the University of Connecticut. I am a PhD candidate graduating this semester, so I'm in the thick of it right now. But today, I really appreciate the opportunity to talk about a Shiny web application that I made. That analyzes paired air and stream temperature data sets to analyze for different hydrologic influences. Notably, I built this to evaluate groundwater influence on streams. However, it can be used for multiple different ways, and we'll get into that a little bit. All right, so the objectives of this web app, the PASTA web app, setting for paired air and stream temperature analysis, was built on this idea to increase accessibility. So this is a relatively simple method comparing air temperature to stream temperature. And we really think that a wider range of stakeholders should be able to use this. And so one of the core underlying reasons for this development was ease of accessibility. How easy can we make it to have anybody use their stream temperature to inform a hydrologic process? So that was kind of the major idea. And then what we want is to then also allow as much stream temperature data as there is out there to be used. There's a lot of unused stream temperature data. Stream temperature is collected for many different reasons. So even if you're collecting other parameters, often you have to collect stream temperature data. And so it can go unused, and then also it is widely available. So we wanted to kind of repurpose stream temperature data. We also wanted to encourage broader use. So this is something that can be used across scales and across times, and is very applicable in many different biomes and regimes. And so, like I said, it's beyond just the idea of using it for groundwater identification. We can also use it for many different reasons. And then, so as far as process goes, this will help us understand hydrologic controls on streams. I use that in broad terms purposefully. I think these tools are just that. They are additional tools to everything, all the other methods that we're using that help identify spatial temporal effects. And we can also start to consider climate effects. All right, so but what is PASA, right? Like this is, I'm kind of going into the objectives of it. But so what it does is it utilizes stream temperature from the data source that you select. So in this, you can upload your own data sets. You can utilize the USGS data sets, and as well as there's Norwest. And so I'm constantly thinking about more data sets that I can add to that and automatically pull for the user. And then what happens is for North America data, you can decide whether you want to pull in air temperature data based on DayMet data. So that is a 1 kilometer squared grid cells that has daily predictions of air temperature simply. Or you can upload your own air temperature data as well. And so, and that allows it to be used beyond North America if you have your own air temperature data. Anyway, so what the two methods that are used within, that are automatically run within this application are annual sinusoid fitting, which will fit us, very simply, will fit a sinusoid to both air temperature and stream temperature, and it'll analyze the similarities and differences as far as amplitude, so how dampened the signals are in comparison to each other, as well as the phase lag, as well as the mean. And these parameters can all tell us something about the stream that we are analyzing. And then also the more commonly used method being just a linear regression between stream temperature and air temperature, and looking at how the coefficient regression is changed through time, and also how that intercept changes can inform us about different hydrologic processes that are occurring. And one of those being how the influence of groundwater. All right, so these two methods can be are applied within this within this Shiny app. All right, and so where does this data come from? I think one of the major things for me in developing the Shiny app was to make it as user-friendly as possible. And so really trying to make it seamless as far as what data can come in. And so from as far as publicly available data, you can use NWIS data, Norwest data. You can also use any of the publicly available HydroShare resources that are available on CUAHSI's website. And then, like I mentioned before, the air temperature, if you choose to use, or if your site is in North America and you don't have your own local air temperature, you can extract the temperature, the air temperature using DayMet, which we already saw a little bit on earlier. All right, so what does the platform look like? So at the top here we have very simply our information page, so a lot more of the citations that you can use to explore the data. Right now I have in review a more of an interpretation guide manuscript, and so hopefully that'll be out within who knows, but a few months. But so this is the NWIS data set. You select the state that you're interested in. You can either do it by map extent or state. Obviously, if it's outside of the United States, you choose, I think, I have provinces in here as well. And so you scan to your area and it'll list all the available stream temperature data that's available in that area for the given time period that you're interested in. You select them, you can pick if you want to download flow data as well, and then you can calculate your thermal metrics. So that again takes the data, fits it, and outputs both a summary of the annual sinusoid fit as well as the linear regression. And it does this for the entire time period that you're interested in, as well as for each year. Because often, especially with shallow groundwater influences, we can see strong deviations from year to year as far as contributions of groundwater or changes in the landscape. So if that's what you're interested in, like there's a lot of opportunities there to just kind of dig into this data, again, beyond the groundwater influence, as I've often focused on for this. And so the gray, all the values in gray represent the annual signal metrics, and then the ones in blue represent the linear regression metrics. And then we also have some guides for data if there's missing data, kind of warning symbols, but you can still use the data in case it's of interest for another reason. All right, and then we also have all the results plots. All these are in Plotly, so they're very dynamic plots. And so you can analyze. So on the left here is the annual signal metrics. We have amplitude. Sorry, I think the y-axis got cut off, but that's amplitude ratio versus phase lag. And so that those metrics and how they relate to each other can inform you about groundwater contributions. And I don't have time to dive into that here, but I'm happy to talk with anyone who's interested in that. And then on the right are a series of figures of the linear regressions with the different colors representing years, which is in the legend that's outside the bounds of this slide. Right. And so that was an example of using the USGS data set, and that provides a lot of accessibility that maybe wouldn't be just a first appearance, especially to different stakeholders. And then additionally, I was pretty passionate about adding a way for anybody to use their own data set, no matter what it looked like. And so I spent a bulk of time just trying to make it as easy as possible to wrangle your own data. And so you're able to upload your stream temperature data, no matter what the site, the format, as long as it's an ASCII, you can kind of figure out what's going on, no matter the date format, whether and whatever units it's in. And then being able to do this for your air temperature data as well. And you then have an output data frame that has air and stream temperature for all the days that are available. And so, and then with that, you can run your analysis, and you get the same output that I showed earlier with the data frame, and then the two figures as well. And so, yeah, I'm happy to talk anything more about this, a little more detail, but yes, I hope that was useful.
All right, thank you so much. We will now enter the question period. We have currently 3 questions in the chat, and once those are addressed, speakers are also free to ask each other questions if you have questions for each other. So the first question came in during Tahir, during your presentation, and they ask, is it still possible and how to work with High River just with your own data?
I'm not sure if I understand the question correctly, but the main purpose of High River is that it provides you access to many high quality data sets at larger scale, only US for now. So I'm not sure if I understand what you mean with your own data. But yeah, HyRiver provides access to many data sets that are provided by like USGS or NLCD. Yeah.
Okay. And if the person who asked that question does want to clarify, you can just type a new question in the Q&A. Next, we have two questions from Pin Shui, and they said, Tahir, thanks for sharing this great tool. I'm wondering how PyGeoHydro is different or similar to the USGS data retrieval package. Is it possible to download other variables such as groundwater table and temperature? Is the first question.
So PyGeoHydro, I try to minimize the overlap with other packages, but PyGeoHydro only provides access to only limited number of NVIS endpoints. For example, only the instantaneous and daily values, and also the USGS stations. But data retrieval provides access to some other data sets that are provided by NVIS. But PyGeoHydro provides access not to only NVIS, but many other data sets that are included that data retrieval doesn't provide access. So I tried to, when I was developing HyRiver, I was trying to make sure that I'm not reinventing the wheel. So I try to cover the parts that are not covered. There are some other packages like Hydro Functions or ULMO. Those are the things that there are some overlaps with the HyRiver packages. I hope you have answered your question. But yeah, regarding the groundwater and temperature, no. But it's the HyRiver provides 3 low-level packages that, if you have some knowledge about web services, you should be able to use those 3 low-level packages to access any of the supported web services. And I provide some examples in the on the website. There are some notebooks that you can follow, so you can see how you can use those packages.
Okay, and this next one is also from the same attendee. Tahir, does PyNHD need to download the entire NLCD land cover data first before subsetting its data based on catchment area?
No, all the services that I provide access to, they let you subset only the data that you require. So it's not going to download the entire data set. It's just going to subset the data for your region of interest.
All right. The next question is for Danielle. What entities are your main data sources? Are these data sets harvested or requested through an API?
Great question. Great question. And to that, both. It depends on the data source that we are trying to serve. Obviously through HydroShare and through the data retrieval, those are API based, and then Norwest is harvested, as well as I'm working right now on gathering Environmental Canada data, which has to be harvested, but I'm hoping that'll be available soon. But so that both, and just depends on the data source, and I'm happy to talk more about that.
Okay. The next is for Tahir. Is there any package like HyRiver available in the R environment?
Yes, Mike Johnson has been doing great work in R. One of his packages is called Hydrodata. So he's been working on that, and he has many other packages. If you go to his GitHub repository or website, you should be able to find many of his projects that are R and provide access to many of the data sets that HyRiver provides.
All right. The next is also for you. Can your package be applied to other hydrologic models such as DH, SVM, SWOT, or VIC?
So the High River doesn't assume anything about the hydrological model. It provides data in formats that you should be able to adjust based on the model that you want. For example, in the case that I presented today, it was just a lump model. So it was just a matter of getting the gridded data and then take the aerial average. But if you have a model like WIC, which is gridded, then you should be able to get the data set in a gridded format, for example, DayMet, or other data sets that you want, and then but you should be able to convert that to a format that VIC, for example, can support. But High River, to answer the question, High River just returns the data in the format that you requested. Either it's a geodata frame, or like a pandas data frame, or a X-array data set or data array. But if you want to work with other models, you should take those data sets and adjust them based on the input of others.
Okay, thank you. Danielle, could you talk a little bit more about how you interpret the metrics computed from your analysis? For example, can you use these metrics to compare groundwater influences among sites?
Yes, yeah, I could talk for a long time about this. So if I don't completely answer your question, definitely reach out to me via email. So it's one of the great tools or great purposes of this is looking at longitudinal changes in groundwater influence, as well as looking at groundwater influences between basins or different watersheds. And so how you interpret the metrics from the analysis. So for the annual signal, so this very simply, the annual signal output, if you have an amplitude ratio of close to 1, that means your air and stream temperature are well coupled. And that implies that there's minimal groundwater influence. That means most of the heat of the stream is being derived from radiative inputs, and there's little other influences there. As that amplitude ratio decreases, you would consider more of an influence of groundwater likely. And also, you can look at the phase lag. The longer the phase lag, the more likely it's a shallow groundwater contribution. So we typically have been using a threshold of 10 days, but that's very it's tough to use a threshold, but that would be more shallow groundwater influenced. And then as far as the linear regression, the lower the slope, the more likely groundwater is influencing it. So you can use both methods to tease out the influences of heat, groundwater heat on stream temperatures. Yes, so I don't take up too much time. I hope that answers your question.
All right, so we have in the chat 2 more questions for Danielle and then a question for Aniruddha. So I'll ask them in order. Danielle, great to see an attempt to increase the scope of accessibility for multiple stakeholder types. Can you speak to the challenges and/or feedback on maintaining different presentations of the same data set?
Great question. And I hope I understand as far as maintaining different presentations of the same data set. A lot of kind of adaptive work in the R-Shiny is how I was able to do that. It's a little, as the funding for creating the Shiny app was part of the Hydro Innovations grant from fellowship from CUAHSI. I kind of went from 0 to 100 and learning how to do R-Shinies. And so it was definitely very challenging, and realizing that simple things kind of took a lot more thought and structure than I had anticipating. I did a lot of just testing on different people and different data sets to make sure it was it worked for what kind of is typically out there and typically used. But without getting into details too much, there's definitely challenges as far as making sure that it was as widely accessible as possible for the different data sets that are out there.
All right, and then one more question for Danielle and then one for Aniruddha. Danielle, can your analysis provide the information about the percentage of groundwater contributed to the stream flow? Can you use high frequency, for example, daily sinusoidal curve to fit your temperature data?
Well, okay, so to answer the first part of the question, as far as percentage of groundwater contribution, that is a really tricky question to get at. Usually with these analysis, it's more of, is there a substantial groundwater input? And that can mean different things for different systems. And often these metrics can be more useful as a comparative metric. So thinking about how groundwater is influencing within, among, between year to year. As far as actually getting a percentage, you would have to have a little bit more of a handle on the heat budget. There are ways to start to get kind of these rough estimates of groundwater contribution. So I do have some publications that I can share that kind of speak to that a little bit, or at least some citations. And then so as far as high frequency, so you say daily, so I think do you mean sub-daily, but diurnal patterns? Right now, this you could, but right now, as far as what the annual signal metrics output, it really relies on that annual signal because we want to make sure we're capturing the seasonal variability. But yes, you could fit, and especially the kind of functions that I use, you would be able to fit the sinusoidal curve to diurnal patterns throughout time.
All right, thank you. Aniruddha, someone asked, I'm having difficulty visualizing the glacier from your diagram. Is the depth measured from the visible surface downward?
Yeah, thank you for the question. Yeah, the depth is measured actually from the visible surface downward. So what happens if you subtract your glacier dim with your glacier thickness, you're able to get the glacier bed topography. And with that, you can do numerous things ahead.
All right, thank you. And Danielle, why do you consider only the influence of groundwater? Why not surface water or declining stream flow? Why not the influence of warming stream temperature? Is it possible to do these things using your tool?
So that's some great points. And I think one thing I want to emphasize is about the tool itself is I built it to think about groundwater influence. However, nowhere in the Shiny app itself is it meant to only look at groundwater influence. So these metrics really are just how different are air temperature and stream temperature. And depending on your system, depending on your flow regime, you can start to think about the variability or what these metrics mean in your own stream. And I really want the tool to be used like that. I see things like urban heat use or dam influences. Those kind of uses are actually really excite me about the tool. So I consider beyond just groundwater influence, but that is like that kind of the underpinning of the original development. You can use it to look at warming through time, especially with the NWIS data set. They have data going back to the 70s, which you can pull from, and we have the DayMet data, I believe, starts in 1980. So if you really, you would be able to look at records that are decadal and see how they're changing through time. So the influence of warming stream temperature is definitely something that this tool can look at if you use it in that way. It doesn't fit kind of a warming trend or anything like that, but I do consider that within. I have a 2021 publication in Nature Communications that talks exactly about the warming stream temperatures. Yes, and so like I said, I really want this tool to be used beyond groundwater influence. So I really appreciate that question.
All right, so we don't have any other open questions in the Q&A at the moment. If the speakers have any questions for each other, feel free to raise your hand and ask them now. Otherwise, we will conclude. So we'll just give it a minute to see if anyone else asks any questions. But otherwise, I want to thank all of our fantastic speakers for coming to present their work today. It's been a real pleasure to get to hear you speak. And it looks like we don't have any new questions coming in. So I'll pass it back to Julia to close us out. Thank you so much for presenting, and to all those who attended.
Thank you everyone for your time. Yes, the webinar will be posted on the CUAHSI YouTube channel, but thank you very much and see you next week for the last installment in the series. Thanks again. Have a good rest of your day.
Thank you.